They don't. The error rate on microchips is fairly high, precisely because they're so hard to manufacture. They are, by a pretty wide margin, the most complex mass-manufactured devices devised by humanity. Some chips fail outright. Some don't work as well as others at speed. And that's how we get different speed chips. Nothing lays flat on the chip. They're complex 3D structures when you zoom in. They are manufactured by insanely sophisticated equipment. They aren't. For instance, Intel does binning on its processors. They have more than one chip now. But in the good old days, the i3, i5 and i7 were all the exact same chip. The only difference was in performance testing. The chips that ended up binned as i3 failed to measure up but were within the tolerances of their i3 line, while the i7 are the best ones. Same with overclocking. Chips which have the performance to be overclocked are unlocked. So the most near-perfect chips ended up as i7K, while the most flawed but still commercially acceptable chips ended up as locked i3s. You'd have to get more specific with exact chips to know what they do with ones that are out of acceptable tolerances. Though, some are destroyed or recycled as much as possible, rather than sold or shipped as lesser versions of the main chip line because their tolerances are very, very strict and specific. At this level, the work transistors are not placed. The transistors are atoms thick and wide and engineered directly into the silicon wafers by doping the silicon in those locations to turn the silicon in that location into a transistor. The process is refined, but thinking there are no imperfections is not correct. Many CPUs you buy are the exact same chip. It just failed at primary tests. So they turn the chip down, maybe deactivate a core, cut out one level of cache, and now it passes a lower test and gets sold as a lower chip. That i5 you buy may not have been planned to be that specific i5. They make it look like there are no imperfections. It not that. They are just real good at not wasting bad chips by selling them as lower tier items. How they are made is wild. There are videos on it. But it works similarly to how old 35mm film is developed on paper with enlargers in dark rooms, but the opposite. In a nutshell, the CPU is built using layers of chemicals that change composition when hit with powerful UV light. A large version of the CPU is printed as a filter in front of this light and then uses lenses that focused much smaller on the surface of the CPU. Then another chemical layer is applied that is slightly different and uses a different filter, and the process repeats. The results are super tiny transistors laid out how they need to be. And as others said, failed chips are thrown out. Poor performing but working chips are sold for cheap. And the more perfect chips are priced much higher. Here is absolutely fantastic video that breaks down the manufacturing process for microchips into semi-Eli 5 concepts. https u2.be/dx9cgrzwd-w C equals 3 PV Fo IVNH3 DZW1HB. Hope you find it as interesting as I did if you have the time to watch it. Chips are made in ultra-clean facilities, and they still have a defect rate high enough to serve as the input into other industries, such as photovoltaics. Monocrystalline solar cells are often made of chip wafers which have too high of a defect rate to be worth slicing up into individual chips. They abrade off all of the chip etchings and convert the recycled wafer into a high-efficiency photovoltaic unit. PV materials don't need the ultra-high purity monocrystalline silicon used in chip manufacturing to work, though the monocrystalline silicon has substantially higher performance than polysilicon PV material. However, it is not cost-effective to make such ultra-purity silicon for photovoltaics. So they take the rejects from the chip industry, which are more than good enough for PV use. and recycle them as PV materials. This is a win-win arrangement. The chip makers don't end up wasting high-purity silicon, and the PV makers don't have to grow monocrystalline silicon from scratch. Wafer world. The rise of silicon wafer recycling in semiconductor manufacturing. https www.wafer-world.com/the-rise-of-silicon-wafer-recycling-in-semiconductor-manufacturing. The tolerances for manufacturing are essentially perfection. Yes, everything is held perfectly level. Yes, the wafers are polished to absolute flatness. All of the machines are mounted to resist any sort of external vibration. You don't dare bring anything containing copper or that touched copper anywhere near the non-copper areas of the factory. It isn't something that someone woke up one day and said, let's make 1 billion transistors for one chip. It was all iterative and learning how to do things better. And better technology created tighter tolerances and more complex and larger designs. And there's still defects, but there's also redundancy built into the design, so you don't have to throw the whole thing away just because a handful of transistors caught a defect. None of them are perfect. Your lower-tiered chip may very well have been a newer higher-tiered chip with too many imperfections. When you hear about overclocking a GPU, it's because they are all different and capable of more than it is limited to. The idea is to push yours as hard as it can go. This is often called the silicon lottery, because you might just be lucky and have the best ever manufactured, or one that just barely makes the cut. Those structure sizes you read, nanometers, used to represent the actual dimensions on the chip. At one point, like 10 years or so ago, it became impossible to shrink much further. So they improved the structures. Marketing still labeled it to be smaller to represent the gain in computing power per chip. How it's done is called optical lithography. And although I did that and could tell you many things about it, better watch some explanations on YouTube first. It's a bit beyond to explain like I'm 5. Note that there still are quite a number of imperfections, which is why they manufacture all CPU, GPU chips to the highest spec they offer. And those chips who can't deliver simply become the lower-tier models. That's the neat part, you don't. Well, of course they try to do it as perfectly as possible. But it's unavoidable. This is why you see the big chip makers designing their chips a lot differently in modern times, compared to how they used to. It wasn't that long ago really, where if you wanted to make the best, fastest chip, you just manufactured the biggest one you can. It's called a monolithic die for that reason. If you take the heatsink off a high-end GPU, you'll find a giant piece of silicon. If you take one off a low-end one, you'll find a small one. Part of what makes a huge monolithic die expensive is if there's a defect on it, they have to toss out, pulling a number out of my hat, 25% of a wafer for the one mistake. But if the wafer is all small chips, they might only be tossing out 5% of the wafer. The new hotness is instead of making one monolithic die, you make smaller chips and connect them together to make up for the fact they are individually worse than a big chip. As for avoiding flaws to begin with, that's more in their black box of trade secrets. There's videos for like 90s era chips on YouTube that can explain some of it, but they were working on much larger process nodes. They don't. I know a guy that made his zillions building equipment that chip manufacturers use to test whether their chips are faulty. Branch Education has an insanely detailed video on the production process. https://youtube.be/dx9cgrzwd-w feature equals shared. There are a lot of imperfections in microchips. If you look at the AMD Ryzen CPUs for example, Ryzen 7 has 8 cores, while Ryzen 5 has 6 cores. During production they make one type of chip, and if all 8 cores are functional, they sell it as Ryzen 7. If only 7 cores out 8 are working, then they deactivate the 7th and sell it as Ryzen 5 with 6 cores. In addition to the other answers, memory structures are built with redundant rows that can be switched in during product testing, so if a fault is found it can effectively be patched. Error correction is used so that temporary errors caused by cosmic radiation and the like are corrected automatically, and this can also correct permanently failed individual memory cells. Let's imagine the chip being made is a city. The city works by getting cars from homes to offices. The homes and offices are connected by many different roads and highways. The city is split up into many similar neighborhoods. When there are problems with a road or neighborhood, those areas are turned off or destroyed. The city becomes less efficient. The city does less work and is slower. Since many cities are made all at the same time to save on costs. Each city is different in terms of efficiency. Cities with 16 working neighborhoods are sold for more, while some cities only one of 16 work cost much less. Each city still takes up the same amount of space. Over time they are able to build more neighborhoods in the same amount of space. They can have taller buildings, skinnier roads and houses. To build the city very fast, there is a giant stencil mold. Each stencil represents a feature like all walls on the first floor. After the stencil is placed, it rains concrete on the ground. Sometimes you need to dig a trench or a valley in the city to put different material. Then they cover what you want to keep. Then flood the city with some acid. If you want a metal highways, they use a projector and blast the surface with metal until the metal gets stuck in the ground. There are a lot of different methods, but it mainly involves a lot of layers of adding and subtracting materials. Hopefully the above explanation gives a different take with less computer jargon. When Intel makes say a 12900K, it might be defective but still work well enough, and so that is where i5s and i7s come from. They are just i9s with defective cores sold as i5s. They grow them one layer at a time, similar to how 3D printing is done at home, but much more advanced. Greater than Eli 5. How are microchips made with no imperfections? They're not. For instance, when they make CPUs, they don't intentionally make the lower tier models. They try to make the highest tier of that type every time. Then check for flaws and imperfections. Lock off the parts that are affected and sell it as a lower tier model. Since the other parts work fine. Microchip scientist checking in. You're right that they're incredibly small, intricate, and fragile. That's why there are thousands of steps involved in the process of creating one. Deposition, annealing, implantation, cleaning, and packaging, to name a few. And typically hundreds of engineers, with each engineer being in charge of only one or a few specific process steps. Basically, each different step of the production process imbues the chip with different property. For example, when annealing reduces the resistance of the device so that electricity can actually flow freely through the part it's supposed to flow through. And so after it goes through the annealing process, the annealing engineer will run a measurement on the chip and see if the resistance on it is currently at the target level plus or a certain tolerance. So say every chip is supposed to have a resistance of 5 ohms. The engineer would check to make sure it was between 4.5 and 5.5 or some other range that was determined through experiments. So you get tons of engineers doing that for hundreds of process steps along the way. And after a couple months, what you ultimately get is a wafer with a bunch of chips on it. Note I simplified everything a lot and used made-up numbers. This is literally the highest tech in the entire world. It's what AI brains are made of. And it's what made Nvidia become a $1 trillion company overnight. I'm pretty sure I've seen the video you are talking about. And I'm sorry to announce you that it's fake. The zoom in was way too much. Basically subatomic level. Edit. Is it this one? https youtube.com/shorts/cpucnv phase. This is actually why you have tiers of microchips. It's faster, cheaper to just make the best microchip you can. Because there are already going to be so many imperfections on it. So the ones that get about this much performance are tier 1. Then 2, 3, 4, and some are just unusable. As someone else has said, photolithography is like film developing. Semiconductor manufacturing is layers upon layers of masking, exposing, etching, and depositing the next layer of material down, built on top of a slice of a perfect crystal of pure silicon. A wafer. There are hundreds to hundreds of thousands of copies of the same die on each wafer. At the scales required, even specks of dust can create a defect, which is why it is done in clean rooms with people wearing head-to-toe suits. The suits don't protect the person from the product or process. Not primarily. They protect the product from the human. Dozens of layers placed on top of each other extremely precisely. Any misalignment or mistake in processing at any step will mean some to all of the dies will be bad. You can't eliminate every potential source of failure. And you can't just look at it visually. So it is electrically tested before it gets shipped to a customer. Does it work like it's supposed to? What an acceptable amount of loss. How many are thrown away? Depends on a large number of factors. But primarily money. How much money you make on each one times how many you sell. If you're Intel, and your part is complex and worth a lot of money, it makes sense to sort out, binning, and sell the ones that aren't perfect, but usable, for less money. But for simpler parts, it either works 100% or it doesn't. Even then, the aim is less than 10% of the parts produced are thrown away. And that's pretty common for a mature device. It's all about statistics. It is technically nearly impossible to make chip wafers with imperfections. There is always a certain error rate spread all over the silicon wafer throughout the making. But if you make a lot of wafers with a ton of i9 chips on it, there are some perfect ones on it. These perfect ones are sold as i9. The slightly imperfect ones are downgraded. Imperfections marked and programmed as unusable gates. Sold as i7. The more imperfect ones as i5, and then there are lots of i9 that are so imperfect that they are downgraded to still make good i3 chips. They aren't. Let me tell you a cool secret. Let's say Intel comes out with a brand new series of CPUs. And they introduce a new i11 chip. The most advanced chip yet. Well, because making microchips is so effing hard, even on a damn automated manufacturing machine, there is a huge amount of errors in them. So any chip that don't fall within, let's say, 15% of what an i11 chip is supposed to be gets marked down to an i9. And they repeat the process. Anything under 15% of the power of the i9 becomes an i7. Then an i5. And then an i3. So what's the difference? None really. They are all made identically, on the same conveyor belt by the same machine, with the same process. But cause it's so difficult to make that jazz. And instead of binning the hella expensive CPUs that did not reach the standard, they turn it down a version number. Again, this is simplified as that just happens if they work in the first place. A good example of this is back in the 90s, when a lower-powered CPU was more popular, and Intel was running out of stock. So they took higher-powered one, shut down the power to the lower one, and sold it at lowered one prices. But what's so funny about that? Well, a guy figured out they could remove that powering down block and get the higher power CPU for the lower power CPU price. It comes down to quality really. And the error rate is way higher than you would think. 15% is also an example number. One of the methods used for making chips is called photolithography. In a way, chip manufacturing borrows development practices from photography. They cut very thin slices of silicone and use it as a semiconductor. Semiconductor is a material that is semi-okay at conducting electricity. Some materials are better than others at this job. Then they add layers on top the entire wafer and use a special film that is sensitive to light and flash it to imprint the design. Then they will add another layer of metal and this covers the wafer completely. Then they use gas and a chemical bath to remove the excess metal and leave only traces where the design was imprinted. Since the work surface is so tiny, they add extra material, then use fancy methods to remove what's not needed. Really basic comparison, but say you drew a smiley face picture with a glue stick. Then dumped glitter all over it and flipped the paper over. You'd be left with the glitter that stuck to the glue, creating your smiley face design. They're not. They make dozens of them at a single go, then put them on chips and test them. If they pass certain thresholds, they meet standards for X-level device. These are cutting-edge technology, and the exact manufacturing processes and ingredients are closely guarded secrets, so it's hard to say what the failure rate is of a given chip, but suffice it to say that it can be quite high. This leads to competitive overclockers saying things like, they won the silicon lottery, when they can take a chip and given enough cooling bring it far beyond its specifications. There are many imperfections in chip manufacturing. About 20 years ago, AMD made a 4-core CPU that had a defect in one of the cores. They disabled the core and sold the CPUs as 3-core CPUs. I had a kit of them and they worked well. Chips are not perfectly smooth. They're only as smooth as necessary. Some chips need to be smoother to function. Some don't. The process that is usually used to smooth them out is called chemical mechanical planarization. They basically cover the wafer in an abrasive chemical cleaner and scrub it repeatedly. This averages out to be pretty smooth. This shit is so funny. I am right now 3 weeks deep into a particle hunt because we have approximately 100 adders after an etching process on one of our tools. 200 mm wafer, 8 inches. Particle size 0.2 to 3.2 micrometers. At least very tiny inches. My process on finding them. 1. I put a full batch into the tool and leave 3 slots empty for particle measuring wafers. 2. I pre-measure specific wafers. Very clean wafers with 0 to 10 particles fresh out of the box. Put them in between the other wafers. Shielding effect and PTHR benefits. 3. Run a specific process. 4. Take the 3 wafers out and do post-measuring. 5. If there are a lot of particles, I change one thing on the process. E.g. turn down N2 flow. Change process temp. And then start at 1 again. I have been in this specific fab for 3 works now doing nothing but this for 10 to 12 hours daily. Also I exchange seals, filters, heaters, valves and everything else that might cause particles. Additionally, I am stuck in a full-body condom, including face covers, gloves, hairnet and special boots which ideally keep all my bodily dirt on me. The tool I am working on is located inside a cleanroom which has maximum of 5 particles of a specific size per cubic meter. Quite a few cubic footsies. To achieve this, everything inside this clean room must be cleaned before bringing it in. The paper is a special fabric. The floors and walls are a special material which does not fume out particles. There is a permanent downflow of air, which means air is pumped in huge quantities through extremely fine filters from the top, and the floor has holes in it so the airflow takes particles with it into the double flooring where it is sucked up and filtered out. As for the etching process itself, holy fuck, that's a huge process with overetching. Plasma, wet etching, masking, stripping. IDK everything about this. They aren't. A mature production run might get 80% yield, meaning 20% are not viable. Out of that 80%, many will have parts of them that don't work. These are sold as cheaper processors. The 6-core processor you buy might actually be an 8-core unit with 2 bad cores. The one you buy without integrated graphics might just be one where the GPU is broken. Still, it's fascinating that we're able to get any that work, considering the sheer complexity of the process and the very tight tolerances. I've always maintained that VLSI fabrication is the closest we've ever come to magic. Well, first, they are made in a clean room to minimize the amount of dust and bacteria that could possibly get onto them. Secondly, a lot of them do get damaged. The final stop on their journey through the manufacturing process is to be tested. And only chips on a wafer that works will be used. It's also not uncommon for an entire wafer to get scrapped if something goes wrong. Some chips also have redundancies, so if a transistor fails, another one can compensate for it. Also, nothing is flat. All of the structures on a chip are atoms thick. You just put down and peel back layers at a time. And there are tens of thousands of layers on a chip. First, you put down all the transistors. And then the second half of the manufacturing process is putting down layers of insulators and wires to connect those transistors as you need them. These layers are so flat because they are so thin. Some processes do produce rougher surfaces than others, but none perceivable by a human. I saw a video somewhere explaining the i3, i5, i7 and i9 on Intel CPUs. They are all the same manufactured CPU. They are rated as such by how many transistors in them actually end up working. So an i3 is basically a badly manufactured i9. Not sure if the terms I use are correct, but that is the gist of it. The difference between an Intel i9 and an Intel i5 is the i5 is an i9 chip with broken, malfunction cores. Check out Branch Education in YouTube for a really good Blender animation video on how they are made. They aren't even some of the best chips that get made still have imperfections. Chips have some of the high failure yields out there really, but there's no way around. They simple make a ton of toss the bad ones. The fail rate can be 30-40%, sometimes higher. The ones that sorta work can get cut down and turned into lesser products. Like maybe a few cores are disabled because they didn't work properly anyways, and sold as a lower-end chip. Even when everything is working, some chips will just outright perform others. This is what people are talking about when they mention the silicon lottery and or chip binning. It's the practice of testing and reserving the highest quality chips for the best high-end SKUs, so there's a variation there no matter what due to the level of precision required during manufacturing. So yeah, a lot of what's being produced literally gets tossed out. Well, they recycle what they can, I believe, and they simply try to charge enough that it outstrips the loss. Usually not a big deal because computers are so mandatory for modern day living that people will pay. If the fail rate gets too high though, it can start to make certain chips unprofitable. They aren't. They're screened after the fact and binned based on the degree of success. It's pretty normal for multiple products in a CPU, GPU lineup to actually be the same chip with larger or smaller portions of it disabled to hit a target spec. Some are perfect, some are broken, some are partially functional. For example, the Intel Core i9s are perfect. Core i3s have a lot of broken parts. Core i5 and i7s are increasingly functional. Intel would like every processor they create to be perfect. But that's not the case. They test them and determine how much of the fabrication went according to plan. If a chip works on day one, it's likely to keep working that way forever. So they just sell the less functional chips for less money. Former semiconductor technician here. Clean rooms is your answer. The air is filtered and moved around the fab in a laminar flow, so everything is moved top to bottom. Nothing floating. All process tools have their own air handling. Every process tool is checked daily to make sure nothing is shedding or broken, as well as that the tool is behaving exactly as predicted. Wafers are never touched by human hands. Also, technology is improved to get the lithography lines as small as they are. They have moved way past the visible light spectrum to ultraviolet, then deep ultraviolet, then X-ray. Who knows what the current light source is that they are using to add to some of these responses. Sometimes it works, but not quite as well as it should. While it may not be the performance of the high-end processor it was supposed to be, it does just fine for the mid-range version of that chip. A long time back, I was adding a new heatsink to a video card I had. It was a Radeon 9700 Pro. I took the stock heatsink off, cleaned the thermal paste off, and saw that the GPU in there was supposed to be for a 9800 XT. So instead of tossing it, they lowered the clock speed, disabled a few cores, and sold it as the slightly older and lower level card. They're not. A lot of chips will be slightly imperfect, but not in a way that affects the functionality. Some have defects that mean they can't be fully used, so parts of them will be disabled. For example, disabling a core in a CPU. Some are so defective they need to be scrapped. Learned something cool the other day regarding Intel's i5, i7, i9 chips. They are manufactured to an identical specification. During the manufacturing process, there will always be some amount of failed transistors that affect how many usable cores are on each chip. An i5 simply has fewer working cores than an i7 after the manufacturing process. An i9 has even more fully working cores than the i7. They scan the chips for imperfections after manufacturing and then package them as an i5, i7 or i9 depending on how many working cores remain. Chips do have imperfections, but designers can mitigate them to some extent. Most of the super advanced chips with tiny transistors use CMOS logic and run on clocks. With CMOS logic, since you have two connections, one to power, one to ground, and your chip is digital, it doesn't hugely matter that the transistors are perfect, have perfect resistance and capacitance and current delivery curves. It just matters that you can set something to 1 or 0 within the clock period. And the double connections help with this. Maybe your connection to power is a bit leaky when off, but it's okay because your connection to ground is still gonna be strong enough to drive your bit to a 0. The clock means that you don't need to set stuff to 1 or 0 at a precise speed. You just set the clock slow enough so that the slowest part of your chip has enough time to get to 1 or 0 within a clock cycle. And if that's not enough, you can redesign that part of the chip to not be so slow. However, there are some side effects. First of all, if your connections are leaky when off, that means your chip will use too much power. This results in more heat and worse battery life. Also, if you reduce your clock speed, your chip will run slower. This may require you to sell the part as a cheaper chip with a lower advertised speed, losing you money. Apple had an issue one year where their iPhone chip was made by two different manufacturers, and the chips made from one manufacturer had worse battery life than the other. Just to add, there's redundancy and tolerance planning in chip design and manufacturing at so many levels. It's very hard to imagine from outside. Basically, every part of the process is going to fail and the whole process is planned to tolerate failures until the probabilities are in acceptable range. To draw an analogy, let's say you're designing a car but your factory is really poor quality, but raw material is super cheap. Nearly free. Now you just know that engines may not come out right from factory. So you put two engines in each car. So the likelihood of one of them working is high. and other is turned off. Inside of each of that engine, cylinders and pistons are very likely to fail. So each engine is designed as a V8 and then at least 6 cylinders of them come out right. Others are just disabled, removed. Then wheels just don't come out circular. So each car is made with 6 wheels and then 2 of them are removed, disabled. Even inside of each wheel, 5 bolts are needed, but bolts fail really fast with use. So just make 8 of them and whole car will run until 4 of them fail. And then in the bolts themselves, 10 locking threads are needed mechanically. But nuts just don't come out right. So make 20 contacting threads and then hope at least 10 of them actually contact. Same with bearings and on and on. And once a car is made, there's really special machinery that can check what came out right or wrong. Now, if V8 comes out as a V8, sell it as a different V8 product. 6 wheels come out right, sell it as a 3-axle truck. And even after this, some cars will still be totally broken. So scrap them. It's an insane game of tolerances, duration and redundancies, until total probabilities add up to give you lots of profitable chips. I didn't realize the failure rate was so high. That makes a lot of sense. Pretty insane what humans have created. There is also reliability testing and burn-in, where they try to weed out the weak chips before passing them on to the customers. Wouldn't that require testing of every chip and placing them into different buckets or bins? And then finding a way of marketing the lower performing buckets such that people think they're getting a quality product? What's the failure rate, actually? What percentage of chips have a fault that requires discarding the entire thing? What is the industry standard rate? So it's selection? They seem perfect because the ones they sell are the ones that work? Wait, that means they mass test them, right? Is that what they call the silicon lottery? It's important to understand flat as a relative term. The wafers are planarized. Ground flat. https www.wafer-world.com/post/the-most-widely-used-planarization-technique-to-polish-wafers. https www.wafer-world.com/post/the-most-widely-used-planarization-technique-to-polish-wafers. To a very high level before starting, and at a couple of intermediate points. Then the etching process applies detail and it becomes less flat, but the total depth of all the features is still of the order of 1 micrometer. That's why you get the cool optical effects. Diffraction of light from the surface features. The failure rate varies depending on what the chip does, the complexity and size of the chip, and a whole slew of other manufacturing factors. Sometimes the passing rate can be near 98%. After they are built, there are expensive machines with custom programs and circuit boards that test every chip that comes out of the factory to make sure only the good parts go to customers. For most simpler parts, it's a pass-fail sort of system. But binning makes sense in some applications, like high-margin parts like Intel microprocessors. You also have chips with multiple cores. They are produced in versions with different number of cores, but the number of version produced is lower than the number of versions sold. The other versions come about when one or more core fail in testing and have cores turned off so that only working cores remain. This is a great explanation. Just to add to that, should the question become, yes, but how do they get any to work at all? Quote, they keep things very, very clean. Whole buildings are designed to be isolated, with special air handlers and filters, so as to remove every last dust particle. People have to gown up in clean suits before allowed in. Even in there are rooms, boxes, machines where only special robots handle the wafers of chips. So there is no hint of human contact. The level of science that goes into cleaning is on a whole other level. And not just speed can bin a product for a lower tier. Some may have sections that fail, but the design is quite modular, so they can be sold as a lower tier product that is defined as having a lower amount of those sections. This is classic in the CPU and GPU space, where products are separated by speed and amount of core building blocks. This is the fundamental reason China is fucked right now with the semiconductor restrictions. They don't have the machines or expertise needed to make this grade of microchip. It's a huge reason why they want to take over Taiwan. Not to mention the type of dedicated workers necessary to develop them. It is why they are having a hard time developing them in the States. Wasn't this partially the manufacturing strategy before 3/5/7 core CPUs? 3-core CPUs were really 7-core CPUs with 4 bad cores or something. Once back quite some years, AMD started marketing CPUs with 3 cores. Why 3? They were actually making 4-core CPUs. But when they tested each core of each CPU, they always or nearly always found one that has problems. So if, say, one core could run only at 2.3 GHz without overheating and the others could run 2.7 or 2.8 GHz without overheating, they'd disable the bad core and sell it as a 3-core 2.7 GHz CPU. I don't know if, initially, they actually sold any 4-core ones or 2-core ones. Far as production, the equipment isn't all that sophisticated. Back in the day, a 486SX was a 486DX with a failed math coprocessor that had the connection between them intentionally severed. Wow, this is very interesting, thanks for responding. I thought this was still the case. Are the different I-S actually different chips now? Greater than they have more than one chip now. But in the good old days the i3, i5 and i7 were all the exact same chip. That's not really true. The general point is true. Binning is done, but i7 takes way more space on wafer, so you don't want to make just them and bin unsuccessful ones. You want to specifically produce i3s too, since they are smaller and you can fit more on a single wafer. Since they are smaller, if there is error during the process it will take out one chip, but you still get more chips per wafer. That's what allows them to be cheaper to produce. From a mass-produced standpoint, this makes so much sense. Aim for all of them to be the best of the best and then assort them based on how many actually work. Thanks for responding. Technically everything is atoms thick. I just watched a video on UV light shooting as you described a couple minutes ago and it's mind blowing. Learned something new today. Oh hey, I have a bunch of these big glass sheets from the 70s that look circuit-like. All have layer #S and are all marked Honeywell. Think this is one of those filters you mentioned? https://imager.com/a/0erv. Saved these from the trash years ago and never figured out what they are. If you interested, Asianometry on YT has very good videos about semiconductor manufacturing. You absolutely should watch this. I work in electronics and my job is designing and programming test boards to test silicon. I knew bits and pieces about semiconductor manufacturing but never the full process like this video. It's amazing. That's super interesting. I had no idea this happened. I always figured that, being mainly silicon and plastics, the residual materials had very little value compared to the energy that had gone into producing the chips. You might like this. Our particle specs for advanced logic nodes are based on 19 nanometers particle sizes. This is a great way to put that explanation. Fantastic response. I had no idea, blows my mind. Greater than, it's an insane game of tolerances, duration and redundancies. What's duration in this context? Greater than now. If V8 comes out as a V8, sell it as a different V8 product. 6 wheels come out right, sell it as a 3-axle truck. I think this is the part a lot of people miss. They make everything the same. Then test and sell it based on how it tests out and what is the most expensive bucket it can fit it. This explanation is so good. I've always wondered why they have so many different models, submodels, or whatever they're called. Overhead seems unbelievably wasteful, however absolutely necessary. I've watched the Asianometry video on chip making and extreme ultraviolet lithography, and it all seems like magic. The fact that it works at all is amazing. The fact that Moore's law exists and they can continue to innovate and improve is mind-blowing. The DRAM I worked on had 90% redundancy. Reminds me of the steel used for Rolls-Royce cars. Not sure about other cars. It is not the best quality steel, but adding 7 layers of paint will make sure it will never rust. Great explanation. Just our best of it. IIRC, isn't this why TI Nvidia cards exist? TIs are the ones that make it through and have the least amount of failures in the fabrication process, thus becoming the highest of the high end. You sell chips that perform well at a premium price, and chips that have flaws that limit their performance at a regular price. Once in a while everything works better than expected at the factory. You're able to produce chips of the better quality in a quantity more than people are willing to pay money for. That's when you can either make it all cheaper to sell, or deliberately disable things in the chip so as to sell it as the cheaper model. Well done. It's worth noting that when you see a manufacturer selling out of a certain high-end bin of a vehicle, say the 3-axle V8, and you start seeing internet comments decrying that they should make more, it's for the reasons explained above why the simply can't. Is this why they say my i9-14900K is slowly killing itself? Yup. Make a 32-core CPU, and hopefully you can sell it as a 28-core CPU. You have a gift, my friend. Explanations. Share it with the world. IIRC. SpaceX did something similar with their guidance systems and not protecting them from gamma radiation. Why spend 100x the amount on a guidance system chip when you can buy off-the-shelf stuff and just put 50 of them on the ship? Barring weight, obviously, but economically it makes more sense to use commonly available components instead of hardening one system. Greater than, but raw material is super cheap, nearly free. Is chip-grade silicon really that cheap by comparison? This is perhaps the best analogy for how chip errors are dealt with I've ever seen. Surely they don't test every single chip, though. So how does that work? Do they have batches that turn out bad or something? Awesome way to put it. I'm not sure if this sort of explanation is strictly true for logic processors. CPU, GPU, basically non-memory sorts of chips. Memory devices are the ones that have all the built-in redundancies, because if a defect kills a sector of memory, they can just turn it off and sell it as a smaller capacity memory chip. If you only need a 4-core chip, you're just buying the 8-core one they were trying to make, with 4 cores that failed due to manufacturing defects. So there's this thing called binning, where after they make the chips they test them and figure out where it best goes for its capabilities. A single design and manufacture of chips will actually be sold as multiple products based on what they can get out of the chips. Things like clock speed, core count, memory, and even features. But sometimes a lower-end bin will sell more than they are making. So they will take some of the higher performance chips, lock out some functions to make it match the lower end, and sell that. For the average user there's no real difference. But back in the day, during the peak of overclocking, you could unlock those features and performance. Not always were you getting an actually higher-end chip and unlocking it would make the chip unstable, but sometimes you'd get lucky. Or there were groups of people who would track serial numbers and could identify a batch as being good to overclock. These days you can't unlock that performance if they lock it away. And my understanding is that binning chips into lower performance segments than what it's actually capable of doesn't happen as much. But the basic binning part is still true. No run of chips comes out 100% functional. They just take what they can get out of it. But there is a minimum level of success they are aiming for. Until they can get that, newer manufacturing methods, making the transistors even smaller, called nodes, are not used for sold products. Failure rate is proportional to area. So the more transistors, the higher the chance each chip will fail. So while they do disable broken parts of the chip and sell them when they can, lower end parts are also made because they are much smaller and you can get many more working parts at a lower per part cost. Per chip failure rate is lower and more chips per wafer unit of manufacturing. Smaller designs have lots of other advantages too. So the salvaging broken large designs is not the primary source of lower end parts. Since transistors are so small, there is a lot of variation in how they turn out. So even if they all work, the chip as a whole may not achieve the intended speed. These chips are sold as slightly lower end parts running more slowly, which relaxes the tolerances on the manufacturing. Source: I'm on the release sign-off chain for one company's processors. There also aren't machining cups. They're using a chemicals and a process called laser lithography that sort of prints it on a die. This is a big oversimplification of it, but it's not really like machining M. Yes, one of the main performance metrics in manufacturing semiconductors is yield, the proportion of chips you manufacture that actually work. https semiconductor.samsung.com/support/tools-resources/dictionary/yield/hash tilde text equals the %20 semiconductor %20 yield %20 is %20a numbers %20 that %20 were %20 put %20 inches. The testing of chips is a whole industry in itself, with companies designing equipment that automatically checks, through lots of different techniques, to see if they have any defects and work as intended. Most chips used are not even in good condition either. For instance, Intel does not produce all the lower tier chips directly. Chips that have cores that don't work properly just get rebranded as a lower tier chip and they disable those cores. That's also the reason chips have to be so small. Let's say your technology is only good enough for 90 errors per one silicon wafer. If you cut the wafer into 100 chips, you only get around 10 working chips. That's way too low yield and the chips would be prohibitively expensive. But if you make the chips half as big in diameter, now you can fit 400 on the wafer and get 310 good ones.